Hello, math fans. I'm making this video on a day where I'm pretty busy. I probably shouldn't be doing this, but it reminds me of this thing that I think about all the time, this proof about the fact that the rationals are countable and the irrationals are uncountable. That's a side topic. I'll talk about that at the end. I'll give a proof of why the rationals are countable. I'll talk about why the irrationals are uncountable. I worry that I've already lost everyone. So if you're someone in my family or friends, listen on. I think it'll be more interesting in a second. What I really want to talk about is this. Each day, I make a list of things to do. Usually the list includes things like this. Answer my email, do the discussion board, ask the teachers this thing on WebAssign where I answer questions, deal with letters of recommendation, prep for the next class if I ever get to that, run errands for my kid, have department service and meetings, and everybody has busy days. But mine just always stays the same. You know, there's not like a day where it's less work. It's just always the same. And I'm sure there's other things here. Correspondence has become a big thing because students can reach me in so many ways. But what happens is this, and this happened today. So the emails, you know, I usually open it, there's 20 or 30. I have 450 students, so there's always something going on. Something's wrong with my seating chart, a grading issue, student in distress. I spend hours and hours thinking about this, and I'm trying to find a way to do it better. But you've got kind of your first email, and your second email, and your third email, and your fourth email, and your fifth email. And today I went to a coffee shop, and I answered emails for about 2.5 hours. And I'm still not done, but I left some of the more challenging ones for later. Okay, then you have things, the discussion board. I haven't gotten to it yet. I probably have a bunch of students. This is what I should be doing right now, is the discussion board. I noticed that I just pulled it up and there's about 15 posts that I need to answer. So you got this list, whatever. I should have put here, this went up to like 20, 30 emails probably today. This goes up to, I think currently there's about 10 things on the discussion board. Each one of those takes a little while to answer. They ask the teachers, people asking for more credit on the homework. I think currently there are about 17 of those that I need to get to. Letter of recommendation at any given time, I usually have about 10 letters of recommendation going, or emails about letters of recommendation. I apologize to those of you that have emailed me and I haven't gotten back to you. Sometimes I let those sit for a week or two. Prep for class. I used to spend most of my time doing that. But now that correspondence has become so big, this used to be like 80% of my time. Now it's like 3% of my time. But let's say I spend a little bit of time today prepping for class tomorrow. Run errands for the kids. So today I went and returned a couple different returns for them. One, basketball shoes didn't fit. I'm going to go pick up my daughter in a little bit. So there's 2 or 3 items there. Usually in the evening there are games. Department service. We have a department meeting shortly. I have some committees I'm on. Right now I'm in actually dealing with kind of a contentious thing. It absorbs my mind quite a bit. Exam solutions, I need to write those up, write the rubrics. That's a few hours of work. Grading, I'm not doing any of that right now, but eventually that'll be, grading usually takes about 8 hours per exam. 4 to 8 hours, it depends on how bad the question is. So I always have these lists of things. And what happens on a given day is I sit down and do my email. I cross these off the list. I get somewhere in here and I'm like, oh no, it's been 3 hours or 2.5 hours. I only have a couple hours left before I have to start doing my kids' stuff. And so then I switch gears and I come to some discussion board stuff, which I'll do in a little bit. And then I'm like, oh no, there's a department meeting. So here we go. I'm 1 hour into that. And then I don't do the ask the teacher. That's what I've been doing this week. I've been just ignoring it because I don't get to it. I did answer about 4 emails about letters of recommendation today. That was probably only 20 minutes. I did all the errands for my kid. I returned the thing. That's priority 1. That took about an hour. I have a department meeting in about 45 minutes. That'll probably take about 45 minutes once it starts. Exam solutions I probably won't get to today. Grading will be next week. This is what a day looks like. I have a feeling a lot of people's lives are like this. You just don't get to the other things. And the next day there's kind of a pile up. So for a number of years, I just work on the weekends. My wife says, why can't you get away? But I just usually catch up on the weekends on emails I'm behind or challenging situations I didn't know how to reply to. Lately, I've been prioritizing this more, but it takes away from other things, and I don't know how to space these things out. I never get my work done. This makes me think of why the rationals are countable. It always makes me think of this. So I'm going to switch to math mode and say something about this, and I'm sure a lot of us can relate about that. I'm sure there are those out there that can suggest better ways. I've been trying to read up on better ways to manage limited time so that you can just be happier about your life. Anyways, and the bad part is nowhere in there did it say Dr. Loveless went to the gym or got in shape. And I've actually gotten quite a bit out of shape. Been having, one of the guys I play tennis with says, you have gotten incredibly fat. You used to be handsome. My friends are not very nice. Okay, anyways, rational numbers are countable. The idea of countable, the idea of a size of a set of things is if you can line them up. So if I have apple, orange, and a banana, we call that three things. Why do we call it three things? Because we can line it up with 1, 2, and 3. Yeah, there's many ways to line it up. We didn't have to call apple 1, but if you can line it up with the set, and a little bit of notation from math, if you can line something up with the set 1, 2, 3, then we say there are three things. I know that's kind of silly, but we try to formalize this in math. So if you can line up sets, we say they have the same size. That's one. Number two, we have this infinite set that goes 1, 2, 3, 4, forever. We call that the natural numbers. This is going to be quick. It's a fairly quick discussion if I'm not doing that many details. It has this funny little N symbol we like to use for it, but it's the counting numbers. We call that set the countable infinite set. So anything that can be lined up with this, we say is countable, meaning you can go 1, 2, 3, 4. The rational numbers, which I forget why we use a Q, I'm sure it's Latin, is the collection of all fractions. Now there's a lot of those. There's like a half, and there's 3/4, and 101 over 71, and a lot of fractions. We say it's a collection of all things that look like A over B, where A and B are whole numbers. B can't be 0, but A and B are whole numbers, even a funny little notation. For now, that's actually only the positives, I should say. Again, I'm being less formal. So the math people, give me a break here. If you're unhappy about my fact that I'm being a little less formal. I've already been joking about my day, so hopefully we can understand where this is coming from. But it's the collection of all fractions you can get. There are a lot of those. Let me show you. So here is the line segment from 0 to 1. And let's make the denominator 2. There are the fractions you get. I should include 0 in here. Let's throw in a 0. Those are the numbers you get if you allow denominators 2. So 0 over 2, 1 over... I'm just going to talk about the rational numbers between 0 and 1 because there's so many of them. Okay, and then if you do denominators 3, there's all the fifths. 1/5, 2/5, 3/5, 4/5, 5/5. That sounds like one fish, two fish, red fish, blue fish. If you keep going and do the ones that have denominator 6, I'm just listing the fractions. Those of you that have ever used a ruler or something, we're just writing the fractions. So if I do it, that's way too fast. I want to slow this down. Slow down this animation a lot. And let's go all the way up to like denominators 50. There are a lot of these fractions. We say that they're dense, meaning it doesn't matter what number you pick. There's an infinite number of fractions, and they're as close as you want to be. It looks like it fills up the whole space. And if you scroll back and look at the whole numbers, 0, 1, 2, 3, 4, 5, it looks like there are way more fractions. Because those are just the fractions between 0 and 1. So it doesn't make sense that you should be able to line up the fractions with the whole numbers. And I'm focusing on positive numbers here, but a similar argument will work if you allow negatives. Okay, back to this. So then the question becomes, well, how in the world are you going to list these fractions? You can't list them in order because there is no smallest fraction. You can't do 1 over 100. Well, there's 1 over 1,000. You say, well, that's not the smallest. I can do 1 over 10,000. And that's not the smallest. So there is no smallest fraction closest to 0. So what do we do? And it's this clever proof that says, well, let's have this be the numerator and this be the denominator. And let's start listing the numbers. Maybe we'll just leave off 0 for now. I'll just list 1, 2. So we're just going to list all, I'm going to try to list all the positive fractions. 2, 3, 4, 5. And this is a classic proof. You'd find this in almost any textbook on numbers or rational numbers or real analysis. But I'm going to make a fraction a over b. So this is going to be 1 over 1. This is going to be 1 over 2. This is going to be 1 over 3. 1 over 4. This is going to be 1 over 5. This is going to be 2 over 1. This is going to be 2 over 2. This is going to be 2 over 3. 2 over 4. And some of you might recognize that several of those fractions can be simplified, but for now, let's not worry about that. 3 over 2, 3 over 3, 3 over 4, 3 over 5. 4 over 1, 4 over 2, 4 over 3, 4 over 4, 4 over 5, and so on. 5 over 1. Imagine you do this forever. That always bothers people. How can you do this forever? You'll never be done. But we're trying to state something here. 5 over 4, 5 over 5. Okay. And what I think about every day when I'm looking at my list of jobs, I am thinking of this diagonalization argument. So math people would appreciate this. And I feel like I am trying to list the fractions by going this way forever, which doesn't work. If I just start listing those, I'm going to miss a whole bunch of fractions. I'm never going to have 5 over 2 or 5 over 3. It's going to be impossible for me to line it up with the whole numbers. And what we're trying to do is line up the numbers, not in order, not in like size order, just any order whatsoever, so that there's a first rational number, there's a second, and it feels like that's not possible. But the issue is there is a way to do it, and it's really surprising. It's a diagonalization argument. So the first number we're going to list is 1 over 1, which is just 1. Okay, so we're calling that the first one. The next one we're going to list, and let me zoom out a little bit. Next one we're going to list is this one. This is a diagonalization argument. So then we're going to do 1/2. Cool. And then the next one we're going to do is 2 over 1, so just 2. Great. The next one we're going to do is we're going to go down to this next column and we'll do this one. Now we're going to get 1/3. Wonderful. And then the fifth one is going to be 2 over 2, but that's 1. We've already counted that, so I'm not going to list it. Then we're going to do 3. And then we're going to do the next one. So then we're going to do 1/4. And then we're going to do 2/3. And then we're going to do 3/2. And on and on and on. And the argument goes like this. Will the fraction, let's just pick one, 77 over 91. Will that be in this list? It will be. It'll take you a long time to get there, but it will be. It's when you get to the 77th row, 77th column, and the 91st row. And we will eventually get there if we just keep diagonalizing. We'll never miss any fractions. Every positive fraction is there. We have just successfully lined up every positive fraction with some whole number. It's really weird when you first see that, but you have so much space to work with. So the rationals are countable. It is possible to list them. That's really surprising. Now they are dense, as I said. So there's different things we can talk about. The fact that they are dense and that they're very tightly packed if you're talking in terms of distance. But if you list, there is a way to, on this infinite number of fractions from 0 to infinity, to point at them and say, I'm going to call that the first one and the second one and the third one. That's kind of like the stars in the sky. Point, point, point. It's countable. So it's a surprising fact about that infinite if you've never seen that before. Now, the problem is, in real life, I can't do this. I wish I could. I wish I could answer one email and then do one discussion post and then another email and then one ask the teacher, and then a discussion post, and then an email, and then a letter of recommendation, and then an ask the teacher, and then a discussion board, and then an email. That probably would be good, but what happens is I sit down to do email, and I just get in a groove, and I keep doing email, and hours go by, and I haven't accomplished the things I need to do. So I need to diagonalize more, and I just have never figured out a good way to do it. So some things I'm just never going to get to. I need to work on it. Or I need to quit and get a job where I don't have so many things to do. Okay, just to wrap this up, the irrational numbers, or all the numbers from 0 to 1, let's just talk about that, is part of what we would say a continuum. So that's saying you have 0 here, you have 1 here, and yes, I know the rational numbers, the fractions, are dense, but I would like to include every number, including numbers like the square root of, I guess the square root of 2 isn't in there, but square root of 2 over 2 is somewhere in there. I don't know, pi over 4 is somewhere in there. And these are ones you cannot write as a fraction, and that's for another video. I'll make a video on why the square root of 2 is irrational. I'll talk about the Greek mathematician who was killed because he proved that this was irrational and couldn't be written as a fraction. That's part of why they thought ratios were rational things. Anyways, that's a different discussion. But let's assume we have every number in that entire thing, which includes some things that are not rational numbers. Here's how the proof goes. Let's assume this set is countable, meaning the set of all numbers between 0 and 1. And we're going to reach a contradiction. This is what we call a contradiction proof. My professor, Ron Vaninkievort, would call it an RAA proof, reductio ad absurdum. I think that's Latin or something. Anyways, we're going to reduce to an absurdity and prove that this isn't possible. So if all our logic is correct, then the assumption is wrong here, and so it must be uncountable. Okay, so we're talking about all the numbers from 0 to 1. If the numbers from 0 to 1 are countable, then there's a way to list them. There's a first number, there's a second number, there's a third number, there's a fourth number, and so on. Just like we can do this. So if we assume it's countable, then it's possible. So here's the bare bones of the proof. I'm not going to talk about every detail, but let's assume we take every number in this list and we give the decimal. I'm just going to give some examples. I'm not saying this is the first one. 6, 3, maybe it just stops there. And the next one goes 3, 2, 1, 4. Maybe that one stops there. And the next one, let's say, is 3, 3, 3 forever, a third. And the next one is, 5, 6, 1, 2, 1, 2, 1, 2 forever. And the next one is maybe the square root of 2 over 2 or something, 0.07156, blah, blah, blah. We just keep going. Here's how the proof goes. I'm going to construct a number that is never in that list, but is a number between 0 and 1. And it's a fairly short proof. It says, whatever the list is, consider the first digit of the first number and pick this digit to be different. Something other than that. And that's always going to be possible. So for example, if it's a 5, maybe I'll just always pick a 1. And then you get to the second one. I'll pick 1 again because it's not 2. Then I'll get to the third one. I'll pick 1 again. I'll get to the fourth one. Let's change this to a 1 just for, if it's a 1, let's have it be something else. Maybe a 2. And then a 1 here. And just keep going, always choosing the next digit to be different from the next one in the list. This is a rational. It may not be rational. It could be irrational, but this is definitely a number between 0 and 1. It may repeat, it may not repeat. We're allowing the not repeating situation, which actually dramatically changes our argument. Okay. We just said that the set is countable, meaning every number is in this list. But this number is a number between 0 and 1, and it's not in the list. It's not the first number because that digit doesn't match. It's not the second number because that digit doesn't match. It's not the third number because that digit doesn't match. And that goes on forever. This matches none of the numbers. This is another type of diagonalization proof, but a proof where you choose things that don't match the diagonal, and because of that, it can't match any of the numbers in the list. That means our assumption is wrong, and that means all the numbers between 0 and 1 forms what is called an uncountable set. Now, questions about the sizes of sets and is there a bigger type of uncountable are historic questions in math. Okay, for math people, that'll interest you. For non-math people, you fell asleep a long time ago. So there's a lot of questions that we could ask here that are foundational to math, but I just find it interesting. Take a course in real analysis if you want to study that more. But this diagonalization thing, I think, is practical. You probably should, if you have a long list of tasks, it probably makes sense to diagonalize your work a little bit so that you can just get to the other things. I personally have been unsuccessful doing that in my life, and so I'll continue to always be behind. And it doesn't help if I make videos like this. But I thought the best time for me to make this video is when I am busy. All right, let me know if you like this video. I have a lot of other things I can say about rational and irrational numbers. I have a long list of videos I want to make on them just for fun for myself. But that's one that lives with me every day, that I can't do what this proof does. All right, hope you find that